In this video, we're going to begin discussing systems of linear equations that have just two variables. And in this video, we're going to talk about how to solve them using the substitution method. So a system of equations is just a set of equations. In this video, we're just going to be dealing with a set of two equations. And we're going to be finding the solutions. So let's talk about what that means. What are we doing when we find the solutions to a system of equations? So the solutions are just the points that satisfy both equations. So I have an example here of a system of two equations. If we were to graph both of these lines, it would look something like this. And if you're in my class, you have this on your notes sheet already. So there's one of the lines. So every point on that line satisfies that equation, meaning if we take a point on that line, we plug in the x coordinate for x and the y coordinate for y, we get a true statement. But not every point on that line also satisfies the other equation. The other equation, the graph looks something like this. And so every point on the red line satisfies the second equation. If we plug the point in for x and y, we get a true statement. But there's only one point that satisfies both equations, and it's the point right there where they intersect. So when we say we're finding the solutions to a system, we're finding those points that lie on both lines, essentially. And lines can intersect once, like we see here, so there could be one solution. If the two equations actually describe the same line, then every point on the line will be a solution. And the third possibility is that the lines are parallel, in which case they never intersect and there are no solutions. So we're going to do a few examples of each. And in this video, we're going to talk about the substitution method. So there's two ways to solve these algebraically. I mean, you can certainly graph it like we did here, but depending on what the equations are, they might be more or less challenging to graph, and if the solution point has coordinates that are fractions or something, that could be somewhat tedious. So there's two methods to solve these algebraically, so just using the equations. And we're going to talk about the substitution method in this video, and we'll talk about the second method in another video. So with the substitution method, the goal is to take one of the equations and solve it for either x or y, and then substitute into the other equation. That's why we call it substitution. If we look at these two equations here, we can solve these for y, but we're going to end up with fractions, right? For the first one, we'd have to divide both sides by 3 to solve for y, and the second one, we'd have to divide by 5. So not that we can't do that, but I think most of us probably don't want to do it that way. We'd probably rather take one of these equations and solve it for x, because with either equation here, we can do that pretty simply. I'm going to take the first one and subtract 3y from both sides to solve for x. And now comes the substitution part. We know that x equals this expression, so we can substitute this for x in the other equation. It's important that we substitute in the other equation. If we substitute it into the same equation we were just working with, we're not going to get anywhere. So we need to make sure we're using both equations. So if we take our 11 minus 3y and substitute it for x in the second equation, we'll have 11 minus 3y minus 5y equals negative 13. And then we can solve this for y. We have a couple of like terms to combine. And then we can subtract 11. And then divide by negative 8. and we get that y is 3. Remember, the solution is going to be the point where the lines intersect. So we need an x and a y coordinate. We just found the y coordinate. So to find the x coordinate, we're going to substitute 3 for y, and we can really use either of the equations because this point will lie on both of those lines. I'm just going to use the second equation, so substituting 3 for y there. We get x minus 15 equals negative 13. And then if we add 15 to both sides, we get that x is 2. And so that point where these lines would intersect is the point 2, 3. So that's the solution. Here's another system that we're going to solve. All of these have a coefficient that's not 1 except the y term in the first one. So that's going to be the easiest one to use if we're going to solve this by substitution, would be to take that first equation and solve it for y. So if we subtract 2x from both sides of the first equation, we get y equals 10 minus 2x. And then we're going to substitute that for y in the other equation. And in this case, we need to distribute now that 5, because it was 5 times y, and y has been replaced with multiple terms. So both terms get multiplied by 5. And now we have a couple of like terms we can combine on the left side. And then we'll subtract 50. And then we'll divide both sides by negative 7. So the x coordinate is 6. And then we'll substitute that 6 in for x in one of the original equations. I'm going to use the first one. So 2x plus y equals 10. So that gives us 12 plus y equals 10. Subtract 12, and the y coordinate is negative 2. So the solution is the point 6, negative 2. All right, this one looks similar to our last one in that we only have one term with a variable that has a coefficient of 1, so that's going to be the easiest place to start is by solving that first equation for y. And then we're going to substitute that for y in the other equation. And once again, we have a 5 to distribute there, so we'll end up with 10x plus 50 minus 10x equals 8. And then when we combine our like terms this time, we have 10x minus 10x, which is 0. And so we actually don't have any variables left. If you end up with no variables left, assuming you've done everything correctly, then that means instead of one solution, it's one of the other two cases. We said there will be one solution, no solutions, or every point on the line is a solution. And in this case, we get a false statement, right? So anytime all the variables drop out, you have a statement that's either always true or always false. This one's always false, right? 50 is not equal to 8. So what that means is no matter what we substitute for x in this equation, we're never going to get the two sides to be equal. And that also means then that there is no point that's going to satisfy both of these equations. And so what we have here is we have parallel lines. So the lines will never intersect, and because of that, there's no solution. So anytime you get a statement that's always false, your system has no solution. All right, with this one, I just keep modifying this problem a little bit. So it's the same equation on the top, solve it for y, substitute it into the second equation. So if we distribute our 5, got 10x plus 50 minus 10x equals 50. So the same thing happens again on the left. When we combine our variable terms, they go away. But this time, we're left with a statement that's always true. If you get a statement that's always true, that means regardless of what you substitute for x and y, you will always satisfy both of these equations. So that doesn't mean we can substitute any pair of numbers for x and y and get a true statement. But what it does mean is that these two equations represent the same line. If you were to rewrite them both in slope-intercept form, they would look the same. We almost did that here. We have the order of the terms reversed, but it was y equals negative 2x plus 10. If you solved the second one for y, you would get exactly the same equation, and so they represent the same line. So again, it doesn't mean any point x, y will satisfy the equations, but any point that's on the line will satisfy both equations because they both give us the same line. So usually what we just write here is that there are infinitely many solutions because this line has infinitely many points since it extends forever in both directions.